Okay, everyone, thank you so much for coming. I hope you're all enjoying the beautiful weather out there today. I thanked Peter for bringing that here from Indiana. So I'd like to introduce Peter Burns to you today. Peter received his PhD from the University of Manitoba, where he worked with Frank Hawthorne. He went on to do a postdoc at the University of Cambridge and at the University of New Mexico. Pretty much since that time, he's been at the University of Notre Dame, where he is the Henry Massman Professor of Civil and Environmental Engineering and Earth Sciences, as well as a professor in the Department of Chemistry and Biochemistry. He is also the director of a number of institutes, the Center for Sustainable Energy at Notre Dame, the Actinide Center of Excellence, as well as the Energy Frontier Research Center for Material Science of Actinides at Notre Dame. So today he's come to share some of his work with us in actinide chemistry and mineralogy, and he's really been a pioneer in this field. So please join me in thanking Peter for coming to share his work with us today.
Good morning. Very happy to be here and have a chance to tell you a little bit about some of our research in recent times. I'm going to start off by emphasizing some pretty basic mineralogy that we've been doing on uranium deposits, and then I'll move into an area of synthetic materials that we've been developing. So uranium is part of the actinide series, which is, of course, normally shown on the bottom of the periodic table. The actinide series arise from the sequential filling of the 5f electron orbitals. They're all radioactive. Thorium and uranium occur in reasonably high abundances on Earth from the original time of formation of the Earth. In other words, their half-lives are long enough that they persist. Protactinium has a much shorter half-life, but it grows in as a daughter product of uranium. So these three occur naturally, and then the rest are only produced synthetically. In my own group, we work with thorium, uranium, neptunium, and plutonium. So only part of our work is with natural elements, about half is with synthetic elements. Anyway, in 1938, uranium was poised to change the world forever, as probably all of you know, but I'm just going to cover a tiny bit of the history anyway. Prior to 1938, uranium was used almost exclusively for coloration. So these are different samples of uranium glass that I have in my home cabinet underneath a UV light, and they fluoresce quite beautifully. This one here is probably from around 1900. The others are much more recent because there are still some producers in the world, although not in the United States. So coloration of glasses and also coloration of various glazes and so on. So that's prior to 1938. The discovery of radioactivity occurred a long time before 1938. It was actually 1896. Henry Becquerel discovered radioactivity when he exposed some photographic film to potassium uranate. So I guess in a sense, this is when the atomic age began, although nobody knew it for quite a while after that. Becquerelite is named in honor of Henry Becquerel. It's a calcium uranyl oxyhydrate. One of the greatest scientists of all time, really, was Marie Curie, and she followed after Henry Becquerel and discovered radium and polonium, both isolated from uranium ores from the Jáchymov district of the Czech Republic. She created the word radioactivity. She won 2 Nobel Prizes, one in physics and one in chemistry, and 3 minerals are named in honor of Marie Curie. Her maiden name was Sklodowska. She was from Poland, and sklodowskite, which is a magnesium uranyl silicate hydrate mineral, and cuprosklodowskite, the copper analog of that, are both named for Marie Curie. And curite, which is a lead uranyl oxyhydrate, is named for both Marie and her husband, Pierre. Anyway, in 1938, Hahn and Strassmann discovered and demonstrated the fission of uranium via neutron irradiation and proposed a chain reaction. The idea wasn't entirely new. I think it dates back to around 1933, But these were the guys that demonstrated it first. They're two German scientists, and of course this occurred not long before the breakout of Second World War. They demonstrated that uranium-235 is fissile and can be split under certain conditions. That only represents 0.7% of natural abundance. Uranium-238 we now know is fertile, which means we can create a fissile element from it in a nuclear reactor, in a breeder reactor if we want. Anyway, uranium changed the world forever because of some simple little physics that is summarized here. Most fuels that we use, wood, natural gas, coal, whatever, we're chemically combusting them and releasing some energy that was stored up in chemical bonds. But nuclear is a totally different beast because nuclear releases energy stored up in a nucleus. And so here's uranium-235, and an incoming neutron interacts with it, forming temporarily uranium-236 nucleus that is unstable, and then it fissions into two, sometimes more, but usually two fission products, much lighter elements, and releases additional neutrons. And there are more neutrons coming out of this reaction than went in, and that thus leads to the possibility of a sustained chain reaction. But what's most interesting about it is if you add the masses on this side of the reaction and you add the masses on this side, which I've done here for the specific case of barium and krypton forming as fission products, there's some probability that they form. There's many other fission products that can form as well. But if you add up the masses, what you find is that going through this reaction, 0.1860 atomic mass units has vanished. And that was the binding mass, and it has been converted via Einstein's equation for theory of special relativity into energy. Energy equals mass times speed of light in a vacuum squared. So this small amount of mass is converted to 173.3 mega electron volts. And that's, of course, the beauty of nuclear. A fuel pellet the size of the end of my finger can easily produce or release as much energy as 3 barrels of oil or a ton of coal or 17,000 cubic feet of natural gas. And that is just a simple once-through fuel process like we use in the United States. If you reprocess the fuel, you can up that considerably, and if you go to breeder reactors, you can up that even more. In fact, you can get about 100 times more energy out of uranium than we currently do in our once-through process. So imagine that. Fuel pellet the size of the end of my finger can produce as much energy as burning 100 tons of coal. So uranium is of great, in fact, unparalleled scientific importance, or societal importance, rather. It is the fuel of nuclear energy for electricity production and naval reactor use. All of our aircraft carriers and many of our submarines are powered by nuclear. It's central to international security and nonproliferation, which is kind of a code for saying it's the fuel of nuclear weapons. And it's essential for medical isotope production, a serious environmental contaminant at many sites that worldwide, really, that related to the fuel cycle and in particular weapons production. So a Russian nuclear sub power plant near my home, and this is actually in Michigan, but Notre Dame is very near the border with Michigan. This is up on Lake Michigan, 2 reactors at this plant. Cartoon representing nuclear weapons and imaging from medical, all depending on uranium. So let's get into a little bit of the crystal chemistry of uranium. I'm especially interested in hexavalent uranium because it's more interesting. It's more fascinating than the lower oxidation state of uranium from my perspective. The hexavalent form of uranium is the stable oxidation state here in the room, anywhere in an oxygenated atmosphere like we're in. And where uranium is hexavalent, it will, if there's any water or oxygen around at all, it will spontaneously form this uranyl ion. And this uranyl ion has uranium triply bonded to 2 oxygen, and it's normally just about linear. These triple bonds are very short, 1.79 angstroms. So this unit is absolutely dominant in chemistry of hexavalent uranium, whether it be aqueous and other solvents or in minerals, etc. This uranyl ion has a formal valence of +2, so it occurs coordinated by additional ligands in crystal structures or in solution. 4, 5, or 6 ligands are the norm, and they're in the equatorial positions of square, pentagonal, and hexagonal bipyramids, where notice those apical oxygens correspond to the uranyl ion oxygens that are triply bonded to uranium and therefore are not very chemically reactive anymore. They don't form strong bonds to high valence cations. They may accept a hydrogen bond or form a bond with sodium or something. So the action in these crystal structures, these minerals, is through the equatorial positions. That's where all the linkages are going to take place. And that will lead to a dominance of sheet structures and to an extent chain structures. So starting a long time ago, people recognized that one can distill a mineral structure into a kind of a simpler form as a binary structure representation. This goes back all the way to the Braggs, who started to develop a classification for silicate minerals based on the linkages of the silicate polyhedra or tetrahedra. So in this concept, mineral structures are made up of a strongly bonded structural unit, which involves the higher valence cations and their coordinating anions, and the bonds between them. So it's a strongly bonded part of the structure. And it's normally anionic. It's sometimes electroneutral, but usually anionic. And most mineral structures, of course there are exceptions, but most also then have an interstitial complex, which are lower valence cations, and very often water, that link the structural units together into the extended structure. So I've used this approach with uranium compounds extensively, and in particular focusing in on the structural units across the different minerals and synthetic compounds. So this is a structural hierarchy that I built a long time ago, 1996 initially, for hexavalent uranium or uranyl compounds, both minerals and inorganic synthetic compounds. And when you do that, the structural units fall naturally into the standard groups, clusters, chains, sheets, and frameworks. There are many important subdivisions and so on within these different groups, which I'm not going to cover today. But in 1996, when I published the first version of this hierarchy, there were 180 such structures known, and the first number in each of these classes represents the number of occurrences of that structure type in that original 1996 paper. And then our most recent version, postdoc and I did in 2016, there's over 750 compounds, and the numbers in the third place correspond to their frequencies of occurrence. You notice that sheets are really quite dominant, and that's because of the linkage through the equatorial positions of those uranyl, hexagonal, pentagonal, and square bipyramids. Anyway, this growth in the number of structures is quite dramatic. In 20 years, growth by a factor of about 4. Most of that's not been in minerals. Most of it's been in synthetic work coming out of half a dozen groups around the world that have really put a big effort in. But some of it does come out of minerals, and that's what I want to focus on for the next few minutes. I've been involved in a decade of work on new uranium minerals. I was very much a mineralogist throughout my graduate studies and relatively early in my career. Worked a lot on uranium mineralogy, but then I kind of got away from that. And the last decade, I've enjoyed the opportunity to get back into the discovery of new uranium minerals. And I'm going to talk about 3 localities. 2 of them are classic localities that if you know anything much about uranium mineralogy, you'll have heard of these localities. And the other one is a new locality. So the first is Jáchymov in Czech Republic. The second is Shinkolobwe in the Democratic Republic of Congo. And the third is Red Canyon in Utah. And it's that third one that's really a new locality relative to new uranium mineral species. So Jáchymov, Czech Republic was, it's a first of all, a granite-related deposit, and it's very metal-rich. It's been mined off and on since something like 1580. This is one of the mines there, which I was in. I took this photo myself. This particular mine is maintained because they have some water pumps in one of the lower levels of the mine to pump water, hydrothermal waters up to the spa systems that attract tourists. So it's maintained, and you can actually walk through it in reasonable safety. Me and my colleagues go into the other ones as well, usually unofficially, in order to gain more samples. One of the great things about this locality, I guess, is that it is where Marie Curie obtained her ore concentrates that were used for discovery of polonium and radium. So this is a classic locality that's been well documented for a very long time. Shinkolobwe, Democratic Republic of Congo, is a metamorphite deposit. It was a very rich deposit that's been mined out, and the mines are flooded, and it's in a war-torn and dangerous country to be in these days. But there's a great collection of minerals that have come out of here, primarily due to the activities of one or two people. And the greatest collection of these resides in Belgium at the Natural History Museum, because Belgium was in control of the Congo at the time when this mining took place. And finally, Red Canyon in Utah, a new famous uranium mineral locality, and it's a sandstone type deposit. It was mined in the 50s and 60s during kind of the height of the Cold War. So I want to focus in on just a few of the new uranyl minerals that have come out of these localities to give you a sense of what we've been finding. And I'll start off with uranyl sulfates. There were only a handful of uranyl sulfates known prior to the current work of the last decade, and their structures were pretty limited in terms of complexity and variability. Anyway, uranyl sulfates form where you have oxidation of uraninite, which is a tetravalent uranium oxide species, and sulfides. Many of these minerals probably wouldn't have formed if mining hadn't taken place. You run a drift through a mountain and specifically go in and mine out areas rich in uranium. Water percolating down through those rocks will then dissolve up some uranium, some sulfur, a sulfate, and where the water enters into the drifts and mine workings, it tends to evaporate because of air moving through and precipitate these minerals. So some of them, although not created specifically by humans, may not have existed without the mining operations. Anyway, we go to these old mines and we crawl into them and we find lots of interesting rocks, sample them, bring them back to the labs and so on. It's a little bit challenging and slightly dangerous because one can encounter old dynamite in these places, and rocks, of course, tend to fall on your head and all those. But anyway, evaporation of acidic water in the mine workings and on tailings, and these minerals tend to be quite soluble. Here's an example, klaprothite. It's a sodium uranyl sulfate hydrate. It's from Red Canyon. It has this structure here, for which this is a structural unit. It's a uranyl pentagonal bipyramid sharing one equatorial edge with a sulfate tetrahedron and 3 equatorial vertices with sulfate tetrahedra. I actually discovered this cluster synthetically about 2001 or 2002, and it showed up. I didn't expect it to show up actually in a mineral, but it in fact did show up in several different minerals very recently. The mineral was named after Martin Klaproth, who was the discoverer of uranium. Actually, he didn't quite discover uranium, but in 1789 he identified uranium as a new element. It turned out he actually had UO2, not pure uranium. Nevertheless, he named it, and he named it after the planet Uranus that had been discovered in 1781. Interesting, in 1940, when the Berkeley group discovered Neptunium and plutonium, they followed that scheme and named those two after planets. Of course, it ended after plutonium. Another interesting uranyl sulfate out of that locality that also has a cluster of uranyl polyhedra is autohanite. It has something you'll recognize right away because that is the the cluster I showed a moment ago, but now they're connected into this slightly bigger unit, 4 times bigger in fact, and then they're connected through the sodium and the water. We named this one after Otto Hahn, discoverer of the fission of uranium in 1938, who I mentioned earlier, a Nobel Prize in Chemistry. There are 5 different uranyl sulfates we found that have isolated clusters. Those are the range, and they're all sodium uranyl oxyhydrates. We've also found a bunch of new chain structures. Fermite is a good example. It's a sodium uranyl sulfate hydrate. It has this chain here. Uranyl pentagonal bipyramids are bridged through 2 sulfate tetrahedra on either side and then kind of decorated by a fifth sulfate tetrahedron. This mineral is named after Enrico Fermi, who was the physicist behind Chicago Pile 1, the first man-made nuclear reactor in the world that operated at the University of Chicago in 1942, that was scaled up by a factor of 4 and put into the B reactor at Hanford, which was the world's first plant-scale nuclear reactor. It was a plutonium production reactor that produced the plutonium that was used in the bomb dropped on Nagasaki, Japan in 1945. So Enrico Fermi. Oppenheimerite, another sodium uranyl sulfate hydrate. Pretty similar structure actually as what we saw in Fermite, except that extra sulfate is not there anymore. Now there's just water at that site. This mineral, named for Robert Oppenheimer, the leader of the Manhattan Project in Los Alamos, New Mexico, that produced the nuclear weapons during the Manhattan Project. So we found actually a lot of different uranyl sulfate chains in these minerals. These are the chains that have shown up, 9 different minerals in the last decade. A couple from Jáchymov, but most of them are from the Rid Canyon locality where uranyl sulfates are particularly abundant. In fact, that's almost all of the new minerals we've found at Rid Canyon. There's 1 uranyl carbonate there, but all the rest have been, and 1 uranyl oxyhydrate. All the rest are uranyl sulfates. Anyway, moving on to sheet structures. Methusiais, it's a mouthful to try to say, is a potassium uranyl sulfate vanadate, which is quite an unusual chemistry to find. It's from Jáchymov in the Czech Republic. It has this really beautiful sheet here. That particular unit was new in a mineral. It has vanadilyl polyhedra right here. That's new in a mineral, but we had actually found it a few years earlier in some synthetic materials I'll show later. Anyway, this one was found by my friend Jakob, who's at the university in Prague, and it was named after this guy, Matthäus, who was an evangelical pastor in Jáchymov in the mining district, and he actually wrote a bunch of sermons about minerals and mining, and I read a couple of them. They're kind of interesting. So he was very important, of course, in the mining operations as he ministered in the camps. Rid Canyonite from Rid Canyon is another sheet uranyl sulfate. This one's an ammonium manganese bearing mineral. It's got some beautiful crystals. The structure has these zigzag chains of uranyl pentagonal bipyramids that share edges, and those chains are linked through sulfate tetrahedra. This is the well-known zippyite type structure. First one of these was discovered in probably about 1908 or 1909. They were studied by Clifford Frundell at Harvard Museum in the 1950s, again in the 1970s, and now they've exploded in terms of species abundance. The zippyite sheet now occurs in about a dozen different species that differ in terms of the interstitial complexes. So this particular one we named for the type locality in Rid Canyon. So here's a summary of the new sheet structures that have been found in the last decade in minerals, where the zippyite group actually corresponds to 4 new species, the zippyite sheet. Anyway, 10 new uranyl sulfates in general, most of them from Rid Canyon, but actually, well, 5 of them are from 5 of them are from Jáchymov. Uranyl carbonates are also quite an important class of uranyl minerals. They tend to form where carbonate is either dissolved from air or is present in the rocks as a carbonate minerals that are dissolved. And when it comes to understanding the mobility of uranium in the environment, these uranyl carbonate species are particularly important, especially in this kind of region here of slightly alkaline pH. Typical groundwater is usually around 8, and so these uranyl carbonate species are quite dominant. They tend to be even more soluble, by and large, than sulfates. First one I want to mention is from Red Canyon, and we named it leozilardite. It's a sodium magnesium uranyl carbonate hydrate, and it has this isolated unit here, which is a uranyl hexagonal bipyramid sharing 3 corners with carbonate triangles. This is exactly the aqueous species that you see above pH of around 8.5 or 9. And it is a constituent of many different uranyl minerals. This one we named after Leo Szilard, who was a physicist, inventor, biologist, and so on. He actually conceived of the nuclear chain reaction in 1933, 5 years before it was actually demonstrated experimentally. 5 new minerals contain the same uranyl tricarbonate cluster, although they're quite different in terms of the rest of their chemistry. 4 of them are from Jáchymov, only 1 from Red Canyon. As I mentioned, almost everything in Red Canyon we're finding are uranyl sulfates. Paddle wheelite, which we just published last week, is an unusual mineral for a variety of reasons. The most remarkable aspect of it is probably that the name is in reference to the appearance of its crystal structure, which looks rather like a paddle wheel, if you have a good imagination, I suppose, where there are uranyl tricarbonate clusters, much like we saw in the simpler minerals, but they're connected through a copper polyhedron. This is a copper square pyramid where the carbonates connect on the base of the pyramid, and then there's another one sitting out here. So this unit is what we reference when we name the mineral paddle wheelite. To be perfectly honest, I kind of dropped the ball on it because my doctoral student Travis Olds was putting together the proposal, and he had paddle wheelite, and I thought he was joking. You all know that if you want to name a new mineral, you have to describe it in a lot of detail, and then you have to submit the application to the Commission on New Minerals and New Mineral Names of the International Mineralogical Association, and they vote on the name and they vote on the species, and if you get it approved, then you can move on and publish, right? So it was at that stage, I thought it was just a placeholder, that we were going to actually think of a proper mineral name, but I was mistaken. Travis submitted it as paddle wheelite, and it was approved. So henceforth, it's paddle wheelite. I probably would have chosen something slightly different, but it's memorable at least. Anyway, a fascinating mineral, pretty complex and interesting. And also from Jáchymov, a mineral which I'm really fond of is ewingite, magnesium calcium uranyl carbonate hydrate, also a mineral that was worked on by my PhD student, Travis Olds. It is an incredibly complex mineral. It has 3 different primary kind of building units, the uranyl dicarbonate, uranyl tricarbonate, and this uranyl trimer. And those connect into a cage, which is 2.5 nanometers in diameter. And this cage, it's got some calcium inside and some water, but these cages are connected into the full structure. We don't yet know if the cages form in solution or if they only assemble during actual crystallization process, but I find it really fascinating. This was a really difficult new mineral description to do because the structure is very complex. The asymmetric unit was huge. I was actually in Prague at a conference on actinides, and it was a really lousy conference, and I got bored, and maybe 1 o'clock in the afternoon, I sent an email, a text message to my friend Jáchymov over at the university and said, I'm at this pathetic conference. Do you mind if I come and visit? And he said, oh, sure. So I went to his home, and he has a room that's full of uranium minerals and microscopes and stuff at his home, and we were looking at them, and he showed me this mineral. He says, this is a new mineral. I know it's fascinating, but I can't do the structure. Would you like to try? And I said, absolutely. So he gave me a little bit in a vial, and I brought it back, and I gave it to my student, Travis Olds, and I challenged him. And Travis looked pretty ragged for several weeks as he worked so hard on this structure. But he did solve it, and the initial structure based on laboratory X-ray data wasn't sufficient, so he went to the synchrotron, advanced photon source, collected it again, and ultimately had a great success. It's a really complicated mineral. It was featured on the front cover of Geology in December 2017. We named it after Rod Ewing. Some of you may know Rod Ewing, a distinguished mineralogist who's currently a professor at Stanford University. Aside from the fascinating cage cluster, something that's really interesting about Ewingite is its complexity. My friend Sergei Krivovitchev is a Russian crystallographer who actually studied with me as a postdoc approximately 20 years ago. And he's gone on to really develop a very distinguished career. He's come up with this idea of structure complexity, where he can quantify the information content of a structure based upon, these simple relationships. And it's interesting to look at how that complexity changes in different mineralogical environments and geochemical environments, different synthetic conditions or whatever. Sergei looked at all the minerals and found that the average complexity of a mineral structure is 228 bits per unit cell. So that's normal. Many minerals are very simple. Many are much more complex. And paulonite in 2013 was the most complex. That's a rare zeolite type mineral named after Linus Pauling, obviously, and had a complexity of 6766 bits per unit cell. But Ewingite essentially doubled that, 12,684 bits per unit cell, and that excludes the hydrogen atoms because we couldn't find them. If we had found them, probably the information per unit cell would be about 23,000. In any case, by far the most complex mineral currently known. Paulonite remains the second most complex. The title of our paper was Ewingite, Earth's Most Complex Mineral. So this is a list of the uranyl carbonates that have been found in the last decade, 7 of them, and that's the Ewingite cluster there. If I failed to mention it, Ewingite and paddle-wheelite both were from Jáchymov, Czech Republic, and the samples were collected by my friend Jakub Plasil. Now moving on to uranyl oxyhydrates. We didn't find as many of these, but some of them are really interesting. In particular, Gautierite is quite a fascinating mineral. It's a potassium lead uranyl oxyhydrate, and this one came from Shinkolobwe. We found this on a specimen that was collected a long time ago because these mines are now flooded and are inaccessible. In fact, it was very likely collected by Gilbert Gautier, who was a Belgian mining engineer who worked in Shinkolobwe. It was strictly prohibited to take specimens out of the site because of the whole operation, mining and so on. The reserves were all secret. This was relatively early in the Cold War. But Gilbert Gautier, being a mine engineer, could pass through the security at the mine without having his lunchbox searched. And Gilbert every day brought specimens out of that mine, and probably virtually every specimen in museums today is from his effort. He passed away in 2006 after a long life. Anyway, we named this mineral in his honor, and he very likely collected it originally. So Gautierite from Shinkolobwe, it has lead and potassium in the interlayer and some water, and then it's got this very complex sheet of uranyl pentagonal bipyramids, and it fit really nicely into a series of complex lead uranyl oxyhydrates that we'd known about for quite a while. The simpler ones are over here, and the much more complicated ones are over here. I'll come back to this one, Wolfendorfite, in a moment. but goethite fit perfectly between fumarierite and vandendriesite, as I'm sure you can all see when you analyze the, well, it's hard to analyze the topologies, isn't it? So I'll do this color-coded simplification, which I think will allow you to see more readily the relationship between the sheet topologies for fumarierite, goethite, and vandendriesite. They're modules of the same structural unit that get progressively wider. So, 4 new uranyl oxyhydrates shown here over the last decade.
I'm going to ask a stupid question. Go back just that one slide. So these polyhedra, I mean, is the uranium in the center?
Yes.
Okay, or is it a UO2 in the center?
No, it's the uranyl ion. So the uranium is at the center. The top and bottom apical oxygens are the triply bonded uranyl oxygen, and then these are the equatorial ones. So, over the last decade, 21 new uranyl minerals, 20 of them are uranyl sulfates from Red Canyon, 13 new minerals described from Jáchymov, and 3 from Shinkolobwe. So, very quickly, the Utah locality is becoming world-class in terms of uranium minerals. And I can tell you that we've got at least 20 more new uranium species from Red Canyon that we haven't completed the description of yet. So as those come out in the literature, funny enough, that here in 2018, a new uranium mineral locality is emerging as the most prolific in all likelihood for new uranium species. So very fascinating. But anyway, I want to switch gears a smidget and talk about some synthetic work I've been focused on for a while. And a lead-in point to that is Wolzendorfite, the lead uranyl oxyhydrate mineral that I showed you a couple minutes ago, the sheet structure of. I did not discover this mineral, but I did solve its crystal structure in 1999. And it is spectacular in its complexity. Notice it's really only made out of uranyl pentagonal bipyramids and uranyl square bipyramids. But you go all the way from here to here before you see a repeat of the topology. That's the primitive unit cell dimension, 56 angstroms. It's really extraordinary for a mineral to have that type of complexity in the asymmetric unit. Anyway, Wolzendorfite, isn't that, it's great. What I'd like to do, or I thought to myself, is do something useful with this kind of complex uranium-based materials. And it's awfully, well, what can you do that's useful with Wolzendorfite? Let's see, you can use it as a paperweight, but you probably don't want a radioactive paperweight on your desk. You can throw it at a rabid dog. It's quite good for that because it's got a high density. If you hit them, it'll hurt. And that's it. Well, put it in a museum and look at it, but that's it, right? You can't do anything with it. So what I wanted to do was take this kind of complexity presented to us by minerals and come up with a way to do chemical things with it. And the inspiration came from a strange place, really. It was this mineral here called studtite. Studtite is quite a rare uranyl mineral that was reported as a uranyl peroxide hydrate. I got really interested in this mineral after it was found growing on spent nuclear fuel in some laboratory tests at Pacific Northwest National Lab. It was reported at a conference. I wasn't at the conference. My student, Carrie-Ann Kabatka, was at the conference. She came back and got me excited about it. And we went to the Belgium Natural History Museum looking for specimens of studtite that we could study because the structure was unknown. And they had one really nice specimen. It was from Wolzendorf, Germany, same as Wolzendorfite, incidentally. But the curator wouldn't let us have any. Fortunately for us, he had a nasty habit, smoking, and he went outside for a cigarette, and we stole some. But you know, a crystallographer, you steal some, that means you put a piece of paper down and kind of shook the specimen a bit, and then just fold up the paper and take it home, because you probably will have enough, and sure enough, we did. So nobody would ever know we took any, but we did, and we solved the structure. And so there's the uranyl ion with the triple bonds to oxygen as before. But here now, this is very unique. It's the peroxide OO bonded 1.47 angstroms or so bond length. So peroxide bridge between uranyl ions. This is a new feature in uranium mineralogy. And furthermore, it's kind of, you can see it's corrugated. So these things are these are water, and there's an additional 2 water in between the chains, and the chains are disconnected through hydrogen bonding, yet the chain is kind of corrugated like this for some reason. And this turned out to be quite an inspiration. It forms under circumneutral to acidic conditions. So we got to thinking, pretty simple, what would happen if we went to alkaline conditions in aqueous systems? So we found out that just combining uranyl from any old source at all, hydrogen peroxide to get our peroxide in there, water, and a base, spontaneously, uranyl peroxide nanoclusters like this would form in the water. This is our most famous, this is U60. It's got 60 identical uranyl polyhedra with 2 peroxide and a hydroxyl edge. It's 2.5 nanometers in diameter. The oxygen on the outside are triply bonded, and the ones on the inside are triply bonded. So they effectively stabilize the cluster on the inside and the outside. And this is the topology of this cluster, where the vertices represent uranium polyhedra, and the lines are links between the uranium polyhedra. And you'll notice it's got 12 pentagons and 20 hexagons. It's exactly the same topology as an Olympic soccer ball, 12 pentagons and 20 hexagons, and it's also the same topology as C60, Buckminster Fullerene. So this is a Fullerene topology uranium peroxide cluster that forms spontaneously in water at room temperature. We have been studying these for a dozen years. Job one is normally to crystallize them and fully determine their crystal structure with standard single crystal X-ray diffraction techniques. But we do light and X-ray scattering, calorimetry, of course, chemical analysis, Raman and laser scattering, and mass spectroscopy to get a better understanding of these materials. We've made over 100 types that we've isolated and crystallized. Some of them have Fullerene topologies like these two. This is U20, which is the smallest possible Fullerene topology with only 12 pentagons. This is U28, a little bit bigger Fullerene topology, so it's got some hexagons in its topology. A lot of them aren't strictly Fullerene topologies because they've also got squares. So this series have tetramers or squares in their topologies. There's one right there. There's a whole bunch of those. When we make these, peroxide is essential. But not all of the bridges have to be peroxide. So this is a hydroxyl bridge right there. So targeting those spots, we can put in all kinds of different linkers. And that's what we've done in these examples where we use oxalate or pyrophosphate as linkers to form more clusters. We can also put transition metals in. That right there, you might recall, is the unit that we saw in that rare uranyl vanadate mineral from Jáchymov a few moments ago. This one also contains phosphate. This is the largest cluster that we've made so far, characterized. It's U124, so it's got 124 uranyl polyhedra, 32 phosphate tetrahedra, and they're connected into 4 distinct cages. So these cages are at the vertices of a tetrahedron, and then there's this intermediate stuff that make a 5-cage cluster. So as I mentioned, we've isolated 100 of these, published about 70 of them, and it's been a lot of work, but it's been a lot of fun. Every one of them taught us new aspects about the chemistry of uranium. Now, these have complexity that's similar to what we had in those uranyl minerals, but now we've got it in the nanoscale where we can do chemistry with it. The largest is about 4 nanometers in diameter. These clusters assemble very rapidly in water, in minutes in most cases, at room temperature, spontaneously if you have hydrogen peroxide. Let me say a couple words about the peroxide. In nature, it forms the reason studtite exists as a mineral is that the peroxide forms by radiolysis of water. So where natural radioactivity from the uranium itself and the daughter products of uranium interacts with water, produces the peroxide. It forms likewise in nuclear waste environments or nuclear accident environments, except in much higher concentrations because the radioactivity is much, much higher. We normally just pour the hydrogen peroxide in to make our lives simple, but we could certainly produce the same through irradiation. So they very rapidly assemble at room temperature. These are dissolved macroions in water. They're not colloidal material. These are dissolved species. And that's a little hard to wrap your head around at first. The tendency is to think of dissolved species being much smaller, but these are dissolved. They're anionic, and the charge is balanced by alkali cations. So U60, for example, the charge is balanced by potassium and lithium. They're stable in water for months to years. We've looked at samples a decade old, and they're stable. This is not what one would generally expect of peroxide materials, right? But these guys are really stable. Peroxide is rock solid when it's shared between two uranyl ions. They're thermally stable in water to 150. They are stable under very high pressures. Done a couple of diamond anvil studies where the crystallinity is lost quite quickly. But if we ratchet the material up to whatever pressure and then bring it back and dissolve up the solid remaining and look at it with mass spec, the clusters are still there. Crystallinity is lost, clusters are not. And they're also stable under very, very high doses of gamma radiation, which is something we're interested in because of applications on the back end of the fuel cycle. So these materials have attracted quite a bit of interest, and computationalists have tackled the problem as to why do they form? And two different groups, in particular, several years ago now, tackled, using density functional theory, the linkage between the peroxide and the uranyl ions. And both of these studies independently concluded that there's a partially covalent interaction that favors a bent configuration. And that seems to be what gives rise to all of these different nanoclusters. This group, well, it was me and my friend Laura Gagliardi at Minnesota. She's the computationalist, and her doctoral student Bess, who's shown here. And the other group that studied this independently, totally unknown to us, was out of Spain, Tarragona, which is up near Barcelona, and a group led by Carlos Bo, and his graduate student is Pere Miro. And it's kind of interesting that these totally independent pieces of work were both submitted to the same journal on June 17th, 2010. It's a strange coincidence. It is indeed. But even stranger, the young woman and young man who did not know each other are now married, and they're both professors at the University of South Dakota. So anyway, these clusters so they're going to name their children U60, U28, U24. The synthesis. So the synthesis is so simple. I can't overemphasize that. You know, you make a carbon buckyball, you need pretty extreme conditions. Make these things, you just need, well, water. So normally we dissolve uranyl nitrate, but you can dissolve any kind of uranium you want, but uranyl nitrate works well. In water, add potassium chloride. That'll yield a pH of around 3.5. Then you add the hydrogen peroxide and it precipitates studtite. Then you titrate in a base. In this case, we use lithium hydroxide. And by the time we get up to about pH 9.8, everything dissolves, and we have a clear solution that's orange, and it bubbles oxygen gas. We captured the oxygen gas and verified it was oxygen gas. So this is the specific synthesis for U60. Now, Pere and Bess, working as a couple, helped us with this study, which was published a couple of years ago. There's much more detail behind it than what I'm showing in this one slide. But ultimately, for the conditions of the synthesis, density functional theory was used to probe the relative energetics of all the different species that might form, as well as reaction pathways. And the computationalists tell us that indeed for this particular species, which has 2 peroxide and 1 HOO, the reaction is favorable to reduce one of the peroxide, produce a hydroxyl-hydroxyl bridge dimer, and then have another peroxide oxidize that bridge to peroxide. And this is stabilized by the presence of countercations. In the absence of countercations, this would tend to dissociate, according to their simulations. Well, I think this might be right, because we do need to have some redox chemistry, because oxygen gas is bubbling out of the vial during the reaction. Right now, we're busy making O17 labeled peroxide so we can put some isotopic labels in and better understand these experiments. I'd really like to do some chemistry with these. So that's U60. And these are the countercations shown with their ionic radii scaled to the same scale as U60. And the hydrated radii of those alkali cations. The hydrated radii may be more important because, of course, these things, we're studying them in water. And the pattern reverses, where lithium becomes the largest if one considers the double hydration sphere around it. Anyway, U60, as I drew it here, would have minus 60 charge, but in fact, countercations are there balancing the charge, and they're probably really important in determining properties. This is a study out of Nyman's group at Oregon State, where she studied the evolution of different clusters as a function of time and lithium to uranium ratio. The only thing I want to emphasize here is that you can get isolated simple species, you can get stud tight, you can get U28, which has pentagons and hexagons, or you can get U24, which has hexagons and squares in its topology, all in the same system. Just different times and different cation ratios. This tells us that the countercations important to stabilize the structural intermediates and charge balance the clusters, but the countercations are not probably templating in any way. So U60 in water, that's where I'm really interested in what one could do with these in different solvents. Has a minus 60 charge, but of course, it's going to be associated with countercations in the solution phase. So in water, there would be 60 lithium and potassium that are associated with it. Some of them are inside the cage, like that one, probably bound pretty strongly to the cage. Some might be further inside and not bound so tightly. Other countercations would be outside and again bound to the cage. Others will be further out and in more of a diffuse layer, more dynamic, but they'll be there. So that if you drew a sphere around this whole thing, you could draw a sphere of a radius or whatever that would contain an electroneutral system. Anyway, so I call it the electrical double layer because if you start at the beginning, at the center of the cluster and work your way out, you first pass through a bunch of cations, so it's positive, and then you pass through the cluster itself, negative, and then back through a positive region. So the question I wanted to ask some time ago was, what really determines the properties of this species in solution? Is it the size of the cluster? Is it the topology of the cluster? Is it the charge of the cluster? Is it the size of the windows in the cluster that can allow things to pass through? Or is it the countercations, mostly the electrical double layer? As it turns out, it's mostly the electrical double layer. The cluster behaves pretty much like a giant charged beach ball, and the chemistry is taking place through the double layer. We demonstrated that by assembling larger objects we call blackberries out of clusters. So using just U60 clusters, we can put different countercations in solution and replace the lithium and potassium that were originally in the electrical double layer and trigger different behaviors of the clusters. So in particular, when we make these blackberry species, they're filled with water, these form in water, they're like a bubble in a way. The anionic clusters are linked through a cation-mediated process of some sort. The size of them strongly depends on the countercation we add. So that tells us something about the importance of the countercations. Then when we used in this study, we used 4 different countercations and varied the temperature. We mostly think the effective temperature determines or impacts the distribution of countercations inside the cage versus outside the cage. And we found really different behaviors, all for the same cluster. This just shows TEM, cryogenic TEM work we did that actually demonstrates the blackberry formation. We added calcium, and then we would crash the solution down to water glass, which is a good imaging medium. 19 minutes after adding calcium, there's a lot of U60s that are isolated, and some are in bigger groups, but by 34 minutes, the full blackberries are there. Okay, so I'm kind of running. I'm going to finish in just a couple slides. I want to just say a couple words about use of these that we're working on. So, uranium spent nuclear fuel. All the commercial spent nuclear fuel in the United States is uranium dioxide, UO2. Some of the military fuels and stuff are uranium metals and so on, but they're all made of uranium, mostly UO2. If you want to reprocess fuel today, you use a process called Purex. It was developed in the late 1940s, and we used it by about 1952. We had a plant running at Hanford that used Purex. It's the gold standard in the world now. You use 8 molar hot nitric acid to dissolve the UO2. Then you put in a very large quantity of kerosene to serve as an organic phase. And you add tributyl phosphate, which the nitrate oxidizes the actinides up to their high valence oxidation states. The tributyl phosphate coordinates them and pulls them into the organic phase so you can execute a separation. You repeat this several times and you end up with a plutonium product and a uranium product. You can separate the uranium and plutonium because their redox behaviors are different, so you can shuttle them back and forth at will, basically, by adding reductants back and forth between the organic and aqueous phase. So, it creates a lot of waste. We know we filled 177 tanks with the stuff at Hanford and 50 at Savannah River. Creates a lot of waste. I dream of being able to recycle spent nuclear fuel with, say, water. And so we've been trying to develop a system to do that. First of all, UO2 is insoluble in water. You put UO2 in water and nothing happens. You might get 1 or 2 parts per million uranium in water if you wait long enough. But if you add hydrogen peroxide and a base, and you form uranyl peroxide nanoclusters in water, they greatly accelerate the dissolution of the UO2. The peroxide on the one hand is oxidizing the uranium +4 to +6, but also it's complexing the uranium into the nanoclusters. So this shows ppm alkali versus ppm uranium in solution. We add the alkali. Uranium dioxide powder is already in the water. We get extremely high dissolution rates of the UO2 in these experiments, and it's a 1-to-1 molar ratio between the alkali cation and the uranium added. The maximum is 440,000 parts per million, which is close to 2 moles per liter of uranium, and that occurs for lithium. This is higher than you can achieve with hot 8 molar nitric acid. So we demonstrated we can very readily dissolve uranium fuel under cluster forming conditions, which is water, a little bit of base, and hydrogen peroxide. And you can dial up the uranium concentration you want in water by the specific countercation quantity that you add. We demonstrated using mass spec and so on that these clusters are present in solution and so on and so forth. But then the concept is, instead of doing a solvent extraction process to separate the constituents of the fuel, couldn't we do a mass-based process to separate uranium from the undesirable constituents? So this is the concept where we have a porous membrane The idea is you dissolve up the fuel, form clusters in solution, and you have many of the fission products and so on as simple dissolved species, and then you do a filtration that rejects the uranium. So we did a demonstration of this with a surrogate spent nuclear fuel, not a real one. And well, it works in the bench scale testing. I can show you lots of details if you're interested, but we went from a surrogate fuel that was 95.2% uranium of the metal content to a product of 99.8% using this filtration method and water. So we think there's other applications too that are emerging in the fuel cycle, but more about those some other time. If you're interested in the cluster part of the work, this is a recent review that came out in Dalton Transactions earlier this year that I did with May Nyman. If you're interested in more detail on the structural hierarchy and uranium mineralogy, I can refer you to the Lucier et al. Paper that came out in 2016. Well, thank you very much for your attention. I very much enjoyed talking about some of our current work. Oh, and I brought some models. You can pass it around and, well, take one. I made these myself with my 3D printer at home. Some of them are U60, the bigger one, and some of them are U24. Or no, sorry, U28, I think, the ones I grabbed. I have a big box of them. I make them all the time. And when I go and give a talk, I just fill my container and hand them out.
Thank you. All right, so we have questions. Okay.
Yeah, it's a really interesting talk. I'm interested to know what is all those uranium mineral in the mine is due to, some of them due to the mining process created that, or is they all natural process?
Yeah.
That's
so. It depends on the locality. Like Shinkolobwe, for example, in the Congo, it was massive UO2 uraninite, but there were oxidizing fluids that moved through thousands of years ago or more, and there are strongly oxidized veins. So those were probably not impacted by the mining operation at all. Somewhere like Red Canyon, on the other hand, water normally percolating down through those rocks would merely encounter more rocks and continue to percolate down, having some dissolved uranium, some dissolved sulfur. But when a mining operation puts a drift through, now you've got air added to the system, a lot of air. And mining companies always, I mean, there's nothing much more important in mining than getting the air moving through the drift. Otherwise, your miners will all die, right? If they don't have any moving air. So the miners knew how to set these things up so that there's a good airflow through. So you go in these old mines and you light up a cigarette or something and you can watch the smoke going. There's usually good airflow because they were designed that way. Well, anyway, as a result, the water coming down through the drift intersects this open air, probably pretty dry air in Utah most of the time, and it tends to evaporate and form minerals. So nothing in the mineral was an additive due to human activity, but creation of the whole was. Probably there could be a scenario where it could have happened naturally. IMA is very fussy about anthropogenically produced minerals. They won't allow them to be named as new species. So that's a scenario, though, where you have, say, added components that are important, whether they maybe are some organic components or something that has been brought into the site that somehow shows up in the mineral, or phases that form due to the alteration of man-made materials. For example, there are a bunch of interesting compounds that form on old brass of shipwrecks, but they don't count as minerals because the brass was man-made. So when we describe these minerals, we're very careful to make it clear what we found, i.e. we found this mineral growing on an old mine wall, so that if people want to argue about it, they can, but we see them as minerals. Did I answer your question?
Yeah.
So you've got three very interesting different types of localities, one being granite-hosted, one being metamorphic, and one being, I guess, a Carlin-type roll front. And so clearly they're different ages and in different contexts. Do you see any significant differences in mineralogy associated, and what are their ages?
So the first most important thing regarding age and uranium mineralogy is that uranium decays to lead. And so in the older deposits, we see many more lead uranium oxyhydrates and lead carbonates and lead this and that. So Shinkolobwe, most of the mineralogy at Shinkolobwe are lead uranyl oxyhydrates, like Gautierite that we described, and also another one, Shinkolobweite, that we just described. It's not been published yet from that locality. So the really old deposits, lead uranyl oxyhydrates are very common, and they're really complex. There's a huge range of them, of different minerals, because the lead and when oxidizing waters come along, I think uranium's a fair bit more mobile than lead is. So with progressive alteration, you see a continuously changing lead to uranium ratio, and of course, as a result, a series of minerals that form. In the locality in I don't know the exact age of the locality at Red Canyon. I don't know the age of the uranium deposits because they're different than the rocks they're in, because, like you said, a roll front that moved in later. But we haven't seen any lead minerals there at all. So it's not that old. And then Jáchymov is kind of partway in between. We do see several lead minerals, but it's not nearly as dominant. So without knowing the age off the top of my head of those deposits, I can guess that Shinkolobwe is certainly the oldest. Yeah.
I saw on a little bit of 60 Minutes last night robots being used in Fukushima. One of them is a swimming robot, and I was thinking that maybe you could get a hold of one of those and get down into the water in the mines.
I wonder, the robots that, I mean, if they're in water, okay, so what I'm thinking, people tried to use robots to go in and take good samples from Chernobyl, but the robots mostly failed. The radiation field was just too high, and it became much more effective just to get some guy to run in. Some older person that wouldn't suffer much cumulative life impact, right, from the radioactivity. But I guess at Fukushima, the water's a really good shield. So you could swim a robot right in there probably perfectly okay without worrying much about radiation field. I mean, we put spent nuclear fuel underwater for the shielding and cooling, but you can walk right up to a spent fuel pool, no problem. I don't know how much water's in the reactors now. I have no idea. Yeah?
So with all these complex minerals with multi-components, do you have any sense which fraction of these are thermodynamically stable ground states versus which are, say, a consequence of kinetic circumstance? And,
well, that's a great question.
And also, just another simple question, how do the clusters fill space in 3 dimensions in the solid? If they do, or they always exist as isolated clusters?
Yep. So the first question was, Oh, yeah. Okay, so, when we got interested in uranium mineralogy in the late 1990s, the main funding point there was Yucca Mountain. Corrosion of spent nuclear fuel in the Yucca Mountain or any geologic repository environment would produce a series of these compounds, and therefore we needed to understand their stabilities, their thermodynamics, so one could predict at a regulatory time frame what the impacts might be. So starting way back then, we began developing thermodynamics of these. I have 5 calorimeters in my labs. We measure heats of formation, enthalpies of formation of them. We do solubility measurements to obtain the entropies. And it's an ongoing process. One of my doctoral students right now is working on the Uranyl Sulfates from Red Canyon. But his task is quite difficult because he has to synthesize them all first in high purity, because there's no point in doing calorimetry unless you know exactly what you've got. So I can't answer your question, but we're working on it. We're working steadily towards a fairly complete database on the thermodynamic properties of these minerals. There's still a long way to go. I think we're maybe 25% done. The second question on the packing. Yeah, so they're spherical clusters. Therefore, at most, you could fill 74% of space by packing them. However, the other constituents in the structure are much smaller, interstitial water and the low valence countercations. So we see them packed pretty loosely in crystal structures where the linkages between the clusters are usually through hydrogen bonds. It depends on the countercations. If we use lithium, for example, usually lithium's got a hydration sphere around it, and then the hydrogen bonds are linking adjacent clusters. If we go with cesium, we're more likely to see direct cluster-cluster linkages through the counterion. And this, of course, has serious implications for the stability of the crystal in air. We normally collect data, single crystal X-ray data at low temperature under nitrogen in oil to avoid the rapid dehydration of the crystals, because that water tends to be really easily lost. That's stuffed all in between. We do see quite a significant portion of the countercations in water are inside the cages as well. Some NMR studies have shown that some of those can be pretty mobile, even just at room temperature in the solid.
Great, thank you. So if we don't have any other questions, let's thank Peter and go to lunch.
Oh, it's okay. I'm glad to see you.
The dehydration process? Well, it's the loss of the water that's located between the clusters primarily. So we see a partial or even complete loss of the crystallinity by X-ray diffraction. The clusters themselves don't. We can verify that with small angle X-ray scattering or